Alright, this is section 1-2, and we're going to start the uncertainty of measurement and significant figures. One thing you have to understand about physics and chemistry is that we're going to be doing a lot of measuring throughout the course of this semester, and that one thing with measuring is that every measurement has some amount of uncertainty, meaning that there's some guessing to it. It's never exactly precise. And so that when you take a measurement, no one is ever going to have the exact same measurement for another person. And the uncertainty comes from the limitations of our techniques, meaning that our devices, of course, we look at it and there's some guessing to it, meaning that we have marks on different devices, and that when we look at those marks, someone may say, hey, I think that's right on the mark, and someone might say, hey, I think it's in between a mark. And so that's why we have this thing called uncertainty, or what I call guessing. So we're going to talk about how when we look at numbers, everyone's going to have the same amount of numbers, and how we round basically in this class, and we call that significant figures. So let's talk about kind of like, for example, a ruler. Rulers have large markings, which are centimeters. So we have like 0, 1, 2, 3. Those are in centimeters. And then the small markings are millimeters. So all these little markings here, those are your millimeters. So this would be like 0.1, 0.2, 0.3, 0.4, and then if you're over here, this would be like 1.1, 1.2, 1.3. So that would be kind of like how you would read a ruler. Now notice, those are what the markings are for ruler, but those are what's marked. Now, you can read centimeters, you can read millimeters, but if we're measuring something, what happens, for example, like if I'm reading this line down here, I look at it and I say, you know, and maybe your eyes see differently, and that's fine. Let's just say, for example, this line reads right in between. Let's say that it falls in between, you know, maybe it's not exactly 3.1. Okay? Well, so I would say, all right, centimeters, so far I think it's 3.1. Well, let's say I want to take a measurement. If I was doing centimeters, I could always read one more place than what I'm talking about. Well, I can guess in between here, meaning that it looks like it's in between this line. Well, I can always go one more place than what I'm talking about. So if I'm measuring in centimeters, I can always do 2 decimal places. So I can say this is 3.10. Now keep in mind that millimeters, that means that this is a smaller unit, meaning that this wouldn't be a 3, this would be 30, right? Because each one of these would be a 1, this would be 1, 2, 3, 4, 5, 6. So this would be, you know, this would not be 3, this would be 30. And this right here would be 31. So this would actually be 31.0. And remember, we want to label. So if I'm measuring something in millimeters, I would go to 1 decimal place. And I think the big thing is that if you get confused on what I'm talking about, just make yourself a notation or put in your memory banks right here, these 2 bullet points. If you are making a measurement in centimeters, I always want to see 2 places after the decimal if you want to get a measurement correct in this class. If you are making a measurement in millimeters, you better have 1 place after the decimal if you want to get it correct. Now, which you'll find out here in a minute, it can be a 0 or it can be a 1. That's okay. Those count. Zeros count. You have to put the 0. So make sure you put it. Now, in order for you and I to say that our measurements are the same, that we are within the same uncertainty of each other. We are always within 0.05 of each other. So if we're making a measurement in centimeters, you and I are going to be, because the last digit that we are guessing is in the tenth hundredth spot, we are 2 decimal spots over, you and I can be off 0.05 of each other and still be okay. So let's say that measurement, this line here that we just made, remember we said that it was 31.0. I'm sorry, that was in millimeters. We said 3.10. Okay. Let's say you looked at it and you didn't say that. I don't know. Maybe you said it was 3.11. I don't know. Are we both right? Well, are you 0.05 away from me? Plus or minus, meaning plus 0.05 or minus 0.05? Yes. So we're good. Because the uncertainty, as long as we're give or take 0.05, we're fine. Same thing for millimeters. As long as we are plus or minus 0.05. That is the uncertainty of a ruler. 0.05 plus or minus millimeters, or 0.05 centimeters. Because we can be off 5. That's the general rule, is 5. Now, for graduated cylinders, if we're measuring liquids, we're going to use something called a graduated cylinder. A graduated cylinder, we read the line called the meniscus. The meniscus is the U-shaped line of a water mark. We read it straight across the bottom of that curved line. So notice that it makes a curve, it's the bottom, that's what we read. Now, there are 2 scales when you read a graduated cylinder. You'll see that there are lines that go all the way across on a graduated cylinder. Okay, these here. And they are numbered with numbers. They're marked with numbers. Sorry, I should make that a little clearer. Okay, that's called the major scale. Okay, the lines usually go all the way around. Okay. The minor scale are the little marks, the little tick marks. Okay. Now, kind of an interesting thing, the reason that they call them graduated cylinders is because these marks are called graduations. So they're graduated and they're cylinder shaped, so hence the name graduated cylinders. So you've got the lines that go all the way around that are numbered. Those are your major scales. And then you've got these little marks here, these little tick marks. So those are your minor scales. So again, just like the ruler, you've got markings that you can read. And then of course you've got this gray spot, these in-between areas that you can't read. The uncertainty is always one more spot than the minor scale. So, if the minor scale is 1 milliliter, then the uncertainty is plus or minus 0.5. Here's how I think about it. You have numbers, right? Like, I have the 100 spot, I have the 10 spot, I have the 1 spot, I have a decimal, I have the 10th spot, I have the 100th spot. It's always whatever spot you're in. So like for this example, I'm right here. Oh, I'm sorry. I'm right here. Helps if I think. I'm right here. It's always the next spot over. So it's right here. It's in the 10th spot. So it would be plus or minus 0.5. Okay. If you were, let's come up here where I have some free space. Again, let's take all our little spots that we have. Think of numbers. Okay. If you were here in the 10th spot, let's go where I wanted to go before. You were here in the 10th spot. Then it would be the next spot over. So it would be right here. So it would be the hundredth spot. So your insert would be 0.05 plus or minus. It's always 5 milliliters, of course. I didn't label down here either. Sorry. Okay, so it's always one spot over. If it was, go back over here. Maybe it was over here. We didn't do any non-decimal ones. Maybe it was like, I don't know, here. Actually, let me go over here. Here, which would be the hundredth spot. So you go over here. It would be 50 milliliters. Because you would go over here, because this is 1, this is 10. Right. This is the hardest thing to understand, I think. This gets really confusing, but you know. Alright, let's do an example of a real life graduated cylinder problem. So you have this meniscus here. Alright, let's go through, let's look at it, and let's go through, let's declare the major scale, the minor scale, what the measurement is, and the uncertainty. Alright, I always start major scale. Look at your numbers. 20, 10. What are those going up by? Well, let's see. I went from 10 to 20. So the major scale is going up by tens. Okay. Alright. Then let's look here. The minor scale are what these little ticks are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 in between. So if this is 10 and there's 10 in between, that means that your minor scale is 1. Now, before I measure the liquid, what I do is I go ahead and figure out my uncertainty, and I think, okay, think again of your numbers. My minor scale is here at 1. The next spot over is the 10th spot. So my uncertainty is plus or minus 0.5 milliliters. That means, and the reason I go and do my uncertainty is that means when I do my measurement here in my liquid, I have to have a spot in the 10th spot. So that means when I go over here and I start and I say, okay, the meniscus reads right here at the bottom. So let's see, I'm at, let's see, that's probably 11, 12, 13, and then it's a little above the 13, maybe, I don't know, I might read it as 13.2. Again, it's what you think it is. So I might write over here 13.2. Okay. So 13.2. So that's your answer. So notice that I made sure that I put a spot in the 10th spot. Okay? Alright, now, what do we need to do this for? Why do we make sure that we have uncertainty? Why do we make sure we have the same digits? Now, that's when we actually look at tools. When we sit down, you have a piece of paper and you're just given general math problems, you're not going to have the measuring devices in front of you. And so we're going to learn how to just do it with math problems. And that's where we have some rules called significant figures. Scientists sat down and said, here are some rules that just make it real easy so that you never have to pick up a measuring device and say, oh, well, this math problem used a 50 milliliter graduated cylinder. This problem used a, ruler. Here are just some rules. But of course, when we do real, labs, you need to make sure that you actually know how to use a graduated cylinder. Alright, so to indicate the uncertainty of a single measurement, scientists use these things called significant figures. The last digit written in any measurement is just considered to be uncertain. So that's your uncertain digit. That was your guesstimate digit. Alright, non-zero integers are always significant. So here are your rules. So anything that is not a zero, so something 1, 2, 3, 4, 5, 6, 7, 8, 9, anything that is not a zero. So I have an example here. So 1, 2, 7, 8, 9, these all are significant. Okay, so 1, 2, 3, 4, 5. So notice there's 5 numbers here, so this guy has 5 significant figures. Alright? So, if it's not a 0, it counts. You count it as a significant figure. Alright? So, numbers other than 0 count. Now, zeros is where it gets a little tricky. Leading zeros. Now, you don't start counting. You think of this as a book. Read from left to right. You don't start counting until you hit a number that is not a 0. Because leading zeros never count. So look at this example here. I read a book. I start here. I read. Look at all these zeros. I don't start counting in here until I hit, oh look, a 2. Now I start counting because the 2 counts, the 5 counts. I have 2 significant figures. Again, look at the next one. I have a 0. I'm not counting. Not counting. Not counting. I hit a 3. Again, 3, 6. The 3 and the 6 count, but all the zeros don't count. So this one has 2 significant figures. You don't start counting till you hit your first non-zero digit. Leading zeros never count. Captive zeros. Captive zeros are significant, meaning that once you have hit that first digit that is not a 0, you start counting those zeros that are caught inside. Think about captive, meaning that they are caught between numbers that are not zeros. Like for example, okay, so we start left. Look, hit a 2, that counts. Hit another 2, that counts. Uh-oh, here's a 0. Now, look though, 5. Those are caught in between. So those are going to count. So we have 1, we have 2, we have 3, we have 4, we have 5. This guy's going to have 5. Down here, uh-oh, starts with a 0. Doesn't count. Keep going. Alright, now I can start counting at the 2. I have a 0, but look, after it's a 5. So it's caught. So that one's going to count. Have a 6. So, caught in the middle. So 1, 2, 3, 4. We have 4 significant figures. Last but not least, one more rule for zeros. Trailing zeros. Here's my little thing, and I know it is not proper grammar. No decimal, no count. No decimal, no count. So, this one right here, does it have a decimal? Meaning a visible decimal. There's no decimal there. That means that those zeros do not count. So this one only has 1. This one here, look, has a decimal. It does count. 3. This one, I hit my first non-zero digit. That means that 2 counts. And then look, it has a decimal, so they count. So 1, 2, 3, 4. Now, the only thing on the decimal count thing is that, or no decimal, no count, that kind of thing, is that you have to hit your first non-zero digit. So look, I haven't hit a digit yet. Okay, I hit the 2. Now, once you hit that 2, everything following it will count. What comes before it doesn't. So the 2 and then those zeros count. 1, 2, 3, 4. So these don't count, but everything else does. This is going to be something you have to kind of practice. The more you practice it, the more you get it. It'll be one of those things that just finally it'll be like, oh, I get it. It makes sense now. Okay. The last rule for significant figures is that if it is an exact number, there's only two situations where you have exact numbers. One is that if it is a equivalency statement, meaning that they have given you the fact that like 1 inch equals 2.54 centimeters. You have looked it up on a sheet and it says that this many equals this many. Not something that you have made up, not something that, it has been given to you on a sheet that says, like I've given you here, 1 inch equals 2.54 centimeters. And those have what's called an infinite amount of significant figures. They go to infinity. The other thing is that if you have exactly counted out a certain number of things, like I have sat here and I have counted out exactly 5 basketballs, that is an infinite number of significant figures. Those are the only two times that the number of significant figures are infinite. And that will make a lot more sense at the very, very end of the semester, almost to the point where we are getting ready to leave the end of the school year. So that is the end of Sig Figs. For just the first part, we will get into how to use them with calculations for part 2.